Let's talk about sequences and series. So a sequence is usually written as a of n, and it is simply an ordered list of outputs, so a of 1, a of 2, and a of 3, that correspond to the natural numbers n, so 1, 2, 3, so on and so forth. Now, sequences are denoted by a general term, which is usually in terms of n. So the most basic one would be something like a of n is equal to n, where the sequence would be 1, 2, 3, so on and so forth. You could also have more complex ones, so a of n is equal to 3 to the n, so it'd be 3, 9, 27. And you could basically have anything, so a of n is equal to 5 to the n over n plus 2 factorial. It's simply an ordered pair of outputs that correspond to this general term. Now, a series is a sum. It's typically denoted as S of n, and it simply means adding up all the terms. So it'll be a of 1 plus a of 2 plus a of 3, all the way until you get to a of n. So the series is simply the sum of a of n. Starting from 1 and going to n. Now, some of these infinite series converge to a finite sum, meaning if we kept on adding terms until n approached infinity, S of n would approach a finite value L. So if you wanted to write this out, the limit of S of n as n approaches infinity would equal some finite value L. And what this means is that our infinite series converges. Take, for example, the most basic convergent series, the geometric series. So if I had 1/2 to the n, as per our formula that you would have learned in pre-calculus, the infinite sum would be a of 1, so 1/2, over 1 minus 1/2, which is just 1. So if I looked at this series and I kept on adding all the terms as n got closer and closer to infinity, the sum would get closer and closer to 1. Now, there are many different tests to see if these series converge or diverge, and the one we just went over was the geometric series test. If I have a geometric series, which means it's the sum of some sequence a of n, where a of n is a geometric sequence, which means it's equal to a times r to the n, and therefore has a common ratio r in between its terms, the series converges, so converge, if the magnitude of r is less than 1. And let's look at why. So the formula for the sum of a geometric series is a of 1, 1 minus r to the n over 1 minus r. Now, if we take the limit as n approaches infinity, r to the n, assuming r is less than 1, goes down to 0. So it becomes a of 1, 1 over 1 minus r. And this would be our infinite sum. However, if the magnitude of r is greater than 1, then this whole term becomes infinity, and therefore the sum cannot be computed. So that is the most basic geometric series test. Now, there's also the nth term test for divergence. Now, this test doesn't prove if a series converges, it simply tells you when it diverges. If the limit, as n approaches infinity, of a of n is not equal to 0, then the series has to diverge. And this makes sense intuitively. If I'm adding up an infinite number of terms, those terms have to become negligibly small, because if they're not, then I'm going to end up with an infinite sum of infinity. Only if these terms go to 0 can the series possibly converge to a finite value. Now, there's also the integral test. Now, if a of n is written with some formula with respect to n, we can also map this to a function in terms of x, and therefore we can take the integral of this function. However, there's two conditions. F of x has to be continuous, first of all, and it has to be monotonically decreasing. And what monotonically means is that it doesn't oscillate or alternate. It's simply continuously decreasing towards 0. So an integral is essentially the same thing as summing up all the terms. So the integral test states that if the integral of f of x converges to some finite value, as x approaches infinity, then a of n is convergent. Let's say we have a series a of n is equal to 1 over n squared. Now, this maps to the function 1 over x squared, which I'm going to rewrite as x to the negative 2. If we were to take the integral of x to the negative 2 with respect to x, it would become x to the negative 1 divided by negative 1, or negative 1 over x. Now, the limit as this function, as x approaches infinity, is 0, because our denominator becomes infinity, and so our overall function becomes 0. So, since the integral of f of x approaches a real number 0, then a of n must converge. Therefore, we can say that 1 over n squared is a convergent series by the integral test. Let's look at another series where we say a of n is equal to 1 over n, not squared. Now, obviously, our function f of x becomes 1 over x, and the integral of this is ln x. Now, as x approaches infinity, this function approaches infinity as well, although slower. So because this integral does not approach a real value L, because infinity is not an actual value, this series diverges by the integral test. Therefore, we say diverges by integral test. Now, the integral test is actually how we prove this next test called the p-series test. Now, this is really a shortcut, but basically it deals with series in the form 1 over n to the p, or, n to the negative p. And it says that if p is greater than 1, it converges. However, if p is less than or equal to 1, it diverges. Now, we just proved two examples of this with the integral test. We said that the integral of 1 over n squared, where p equals 2 greater than 1, converges, while we said that 1 over n, where that fits this condition, diverges by the integral test. And it's the exact same thing for any other value. If this p is less than 1, say it's 1 over n to the 0.5, when we integrate it, it's going to be n to the 0.5. And no matter our coefficients, no matter if it's negative, positive, whatever, this term is still going to tend to infinity, and therefore our integral won't converge. However, if p is greater than 1, so like 1 over n cubed, when we integrate, it's going to become 1 over n squared, or any other number. But the point is, since n is still in the denominator, this is still going to converge to 0, or some other coefficient that we may have up here. So the p-series test is just a very simple shortcut for comparing series of this form. Now let's look at the two comparison tests. Firstly is the direct comparison test. And this is pretty simple. It's essentially the squeeze theorem. Let's assume we have two series, a of n and b of n, and that a of n is less than b of n for large n. Now remember, it doesn't really matter for small n because we're dealing with infinite sums, which means n is going to be very, very large. Therefore, since a of n is always smaller than b of n, if b of n converges, a of n must as well. Imagine this is a graph for s of n of b of n, and as n approaches infinity, this graph approaches a certain value. Now, if we were to look at the graph of a of n, since the terms of a of n are always smaller, we're going to be adding smaller numbers, and therefore, s of n for a of n is going to be smaller. So the most it can be is this same limit, because it's bounded by b of n for large n. Therefore, if the larger of two series converges, the smaller one must also converge, and the opposite is also true. If a of n, which is the smaller series, diverges, b of n must as well. This also makes sense if we look at the graphs. Imagine the infinite sum of a of n reaches infinity, so it keeps going upwards. If b of n is above a of n, because it's always larger than, there's no way it can converge to a single value. It must stay above this continuously increasing function, and therefore b of n must diverge as well. Let's look at an example for the direct comparison test. Let's suppose our series is 1 over n squared plus 3. Now, for very large n, the n squared term will be dominant. However, n squared plus 3 is always going to be greater than n squared, because n is just an integer. And therefore, we can say that 1 over n squared plus 3 will always be less than 1 over n squared. So we're going to say that this is our a of n, this is our b of n. Now, thanks to the p-series test, since 2 is greater than 1, we know that b of n converges. And we know that a of n is less than b of n, and b of n converges. Therefore, a of n must converge as well. Here's another example. Let's suppose our sequence is 1 over n square root times the natural log of n. We can directly compare this to a similar series where you say b of n is equal to 1 over n natural log of n. Now, if we wanted to find the convergence or divergence of this series, we can simply integrate it, and this becomes natural log of n. Now, as n approaches infinity, this series also approaches infinity, although much slower. So therefore, this one diverges by the integral test. For large n, square root of n is going to be less than n. Therefore, this one is going to have a smaller denominator than this sequence, and we can say that a of n is greater than b of n for large n. Now, through the direct comparison test, remember, if the smaller series, which here is b of n, diverges, the larger one must diverge as well. So therefore, we can say a of n diverges by the direct comparison test. The second type of comparison is the limit comparison test. Now, this also assumes that we have one series, maybe that we're not familiar with, and another series, b of n, that we are more familiar with. And this says that if you take the infinite limit, so as n approaches infinity, of a of n over b of n, or the other way around, it doesn't matter, if this limit is equal to some real number L, then a of n and b of n have the same convergence or divergence. Let's look at an example where our a of n is equal to 3n squared plus 5n plus 3 divided by 2n cubed plus 4n squared. Now, since this top degree is 2 and this bottom degree is 3, at very large values, I'm going to say this behaves like a sequence b of n is equal to 1 over n. So now to see if they have the same convergence or divergence, we're going to take the infinite limit, so as n approaches infinity, of this ratio. So I'm going to say 1 over n divided by, and I'm going to flip the fraction, so 2n cubed plus 4n squared over 3n squared plus 5n plus 3. Now, the degree is going to be here 1 plus 2, so 3 degree in the denominator and third degree in the numerator. The coefficients are 3 and 2, so for very large values of n, these smaller degrees of n don't really do anything. So this limit is going to be dominated by the 2n cubed and the 3n cubed that we have in the numerator and denominator. And this limit, as n approaches infinity, will be equal to 2/3. So since 2/3 is a real value, it's not an infinite or does not exist, we can say that these two series will have the same convergence or divergence. And from the integral test or the p-series test, we know that b of n diverges. We therefore know that a of n must diverge as well. Now let's talk about the ratio test, which is one of the most important. Now, the ratio test also relies on a limit, but it doesn't rely on two sequences. It simply takes the limit as n approaches infinity of a of n plus 1 divided by a of n. Intuitively, in any sequence, a of n plus 1 has to be smaller than a of n. That's the only way that the terms can go to 0 and the series can possibly converge. So, if this limit is less than 1, it converges. If this limit is greater than 1, it diverges, and if this limit equals 1, the test is inconclusive. Now, the ratio test is really useful when you have sequences that have exponentials or factorials. So we're going to look at a sequence that has both of them. Let's say a of n is equal to n plus 1 factorial divided by 3 to the n. Now, we have to take the ratio of a of n plus 1 over a of n. So let's write that out. Now, a of n plus 1 is simple. You just replace n with n plus 1. So that becomes the limit as n approaches infinity of a of n plus 1 is going to be n plus 1 plus 1, so n plus 2 factorial, divided by 3 to the n plus 1. Then I'm going to flip the fraction, so it becomes 3 to the n over n plus 1 factorial, because that's just a of n. Now, the thing about factorials is that n plus 2 factorial is just n plus 2 times n plus 1 factorial. So this n plus 1 factorial and this one are going to cancel out. 3 to the n and 3 to the n are going to cancel out, leaving just 3 to the 1. And so this becomes n plus 2 divided by 3, because all the other terms canceled out. And it's the limit as n approaches infinity. Now, because n is in the numerator here, this limit is just going to equal infinity. And since it's not a real number and it's definitely not less than 1, we're going to say that this series diverges by the ratio test. Now, if we were to flip the series, so we would say it's 3 to the n over n plus 1 factorial, this series would converge. And let's use the ratio test again to prove it. So it becomes the limit as n approaches infinity of 3 to the n plus 1, n plus 2 times n plus 1 factorial times a of n. So this cancels out. All of these terms cancel out, and you're left with 3 over n plus 2 as an infinite limit still, and this goes to 0, and since 0 is less than 1, this series converges by the ratio test. Now, there's also the root test, which is also sometimes used for exponentials. So this simply says that you have a of n, you have to take the nth root of it, and you have to take the limit as n approaches infinity. And if this limit is less than 1, it converges, greater than 1 diverges, and equal to 1, use a different test. Let's look at an example for the root test. Let's say that a of n is equal to n cubed over 3 to the n. So we have to take the infinite limit, so as n approaches infinity, of the nth root of n cubed over 3 to the n. Now, 3 to the n, nth root is just 3, so I'm going to simplify this down to n to the 3 over n over 3. Now, this 1/3, we can just take it aside since it's just a coefficient, so we'll take it out of the limit. So now what we have is the infinite limit of n to the 3 over n. And what I'm going to do is I'm going to rewrite this so I can use L'Hopital's rule. So this becomes e to the ln, n to the 3 over n. Therefore, e to the 3 ln n over n. And now I can use L'Hopital's rule. So this becomes 3 over n over 1. As n approaches infinity, this approaches 0, and e to the 0 is 1. Therefore, this part approaches 1, and my overall limit is 1/3. Since 1/3 is less than 1, this series converges by the root test. Finally, there exists the alternating series test. Now, an alternating series is anything that has -1 raised to something n. So it could be -1 to the n plus or minus 1, 3, 5, whatever. Whenever you see a term that looks like this, know that your series is going to be alternating, and then you will most likely be using this test. So any series that's alternating, meaning it has this times some other thing, we can write this other thing as b of n. So we can say a of n was equal to some term like this times b of n. And the alternating series test says that if b of n monotonically decreases to 0, remember, monotonically means it doesn't change direction, it doesn't oscillate, it doesn't do anything but just decrease to 0. If b of n monotonically decreases to 0 and is continuous and everything, the series will converge. Now, an important distinction here is that b of n does not have to converge itself. It simply has to meet this requirement. So an example of this would be -1 to the n over n. Now this is just -1 to the n times 1 over n. So this is our b of n. Now we note through the integral in p-series test that this series diverges. However, it's perfectly continuous, and it is always decreasing, and the infinite limit is 0. So overall, this alternating series would actually converge. And the reason this is that when we look at the series 1 over n without this alternating term, we're always adding positive values, because n is always a positive value. However, when we add this -1 to the n term, if every other term is negative, there's something to bring the total sum down, because every other term will be adding a negative. Now remember, because the only difference between a of n and b of n is that sometimes a of n alternates between being negative, we can say that the absolute value of these two series are the same. This also lets us classify what type of convergence these series have. So if you have a series such as the one we just showed, where it's -1 to the n over n, this series converges. However, the absolute value of this series, which is just 1 over n, diverges. As a result, we say this series is conditionally convergent, where only the alternating version of the series converges, and not the absolute one. If the absolute value of a series converges, so if we had -1 to the n over n squared, not only does this converge, the absolute value of this series, which is just 1 over n squared, also converges. And therefore, we say this series is absolutely convergent. And therefore, it is also convergent. So here's a table to remember. Absolutely convergent means the absolute value must converge, and therefore, the regular value must converge as well. Conditionally convergent means that the regular series, which may be alternating, so it may have those negative terms to help bring the overall sum down, may converge, but the absolute value won't because all the terms turn positive, and so the sum grows bigger. Convergence simply means that a of n converges, and it doesn't say anything about the absolute value. It's important to recognize that if a series is absolutely convergent, so if the absolute value converges, the overall series therefore must be convergent. Now let's look at one more example. Here we have cos pi n over n. Now this doesn't look like an alternating series at first because it doesn't have that -1 to the n term, but let's look at our first few terms. So if we plug in n equals 1, we'll get cos pi in our numerator, which is -1. If we plug in n equals 2, we get cos 2 pi, which is +1. If we keep going, we get 3, we'll get -1, 4, we'll get 1. This actually alternates between 1 and -1. Therefore, this series is the same as -1 to the n over n. Now, we know overall that this series converges, and we know that its other series, its absolute value, -1 to the n over n, which is just 1 over n, diverges. Therefore, since this alternating series converges and the absolute value diverges, this series would be conditionally convergent. Now let's look at the error bound for alternating series. Remember that the terms of an alternating series will alternate sign every term. So our first term might be positive, then we'll have negative, positive, negative, positive. Additionally, they must also, since the series has to converge, decrease in magnitude, so get closer and closer to 0. Now, what this means is that our S of n, as we keep adding more and more terms, is also going to oscillate. So, in our first term, our S of n is going to be equal to our A of m, and then we're going to subtract a smaller number. So it's going to decrease slightly. We're going to add an even smaller number, so it's going to increase slightly, and then you keep repeating the same process. So our S of n will look something like this, where it'll eventually converge to a single value. This eventually goes to some value s. Now let's plot our value s here. So we know that, assuming the first term is positive, it can be negative, and therefore your whole example is flipped, but let's assume it's positive. So our first S of n is going to be S of 1, and it's going to be larger than S of n. Why? Because the first thing we do to get a more accurate approximation from S of 1 is we subtract something. Therefore, our first term is greater than S. Our second term, we subtract something, and therefore it becomes less than S. So this will be S of 2. Now we keep going back and forth. Our next term will be up here. This will be S of 3, which will once again be an overshoot, and then we'll have S of 4, which is an undershoot. So while we keep getting closer and closer to the actual S of n, we keep alternating between having an overshoot to an under, to an overestimate to an underestimate. And what does this mean for the error bound? Well, let's list one important fact about series. A series is adding up all the terms. The series up until the n plus 1th term is equal to the series up until the nth term simply plus the next term. And this also means that the difference between the S of n plus 1 and S of n is equal to this n plus 1 term. Let's look back at our graph. So we went from an overestimate to an underestimate by going from S1 to S2. And now, from this equation, we know that the difference between S of 2 and S of 1 is actually equal to A of 2. So we can say that this difference over here is A of 2. Similarly, if we look at S of 3 and S of 4, we can say that S of 4 minus S of 3 is equal to A of 4. So that's this difference right here. Let's draw this out once again. So we have our actual value S and our two approximations, S of n and S of n plus 1, one of which is an overestimate, one of which is an underestimate. Now, we know that the distance, or the difference between the two terms, is A of n plus 1. And note how this A of n plus 1 is always greater than this difference, which is our actual error, because the error in our approximation is the difference from the actual value minus our approximated value. So if we were to graph another S of n, we'll call this one S of n plus 2. The difference between S of n plus 1 and S of n plus 2 would be A of n plus 2. Now this has to be greater than the difference between S and S of n plus 1. And this directly gives us our error bound. if we approximate the sum with n terms, so I'll say n terms, then our error, which is our exact value minus our approximated, is bounded by this magnitude of a of n plus 1. Because if you look at this demonstration, since they have to alternate between undershooting and overshooting the exact value, there's no way that this difference can be smaller than the actual error. And therefore, our error is bounded by the first unused term in our approximation. If we have an alternating series a of n, and we approximate the sum with n terms, so s of capital N, the error bound, so has an error bounded by the first unused term, which will be a of n plus 1. So if I calculated s of 12, this will mean I'm adding up all the terms from a of 1 to a of 12. And therefore, our first unused term, or a of n plus 1, will be a of 13. This means that our error bound, so our s minus s of 12, the magnitude of this error will have to be less than or equal to a of 13. And this is very important because this allows us to know how close our estimate is to an answer. Because these are all infinite sums, if they don't have very precise answers, it's good to use precise approximations instead.